let's see some example how we can utilize all this machinery behind the equivalent martingale measure. Now, the first example is here that we can say we choose a money market account as a numeraire. So what is a money market account? A money market account is an account where initially you have, say, a value of $1, and that instantaneously that value, that there's no random change of the value, then your value of the account at a future time is really just the future value based on this, continuous compounded at the risk-free rate of R, that will give you the future value of this account. So this account starts at $1 and then grow at the risk-free rate. So this is the money market account. Now, if we use the money market account as the numeraire, then when you have some derivative asset F, the price of F at time 0 divided by G0 will just be F0, F naught, because G naught is just 1. And here we have Ft divided by Gt, but Gt is e to the power of this integral, and if we just move it here as a multiple, then it becomes e to the power of minus of this integral. So under the Black-Scholes Merton framework, the risk-free rate is constant, and then if it's constant, you can actually move this out of the integral there, and so it becomes instead of e to the power of minus the integral between 0 to the big T r dt, this part, it just becomes e to the power of minus RT, which is this integral here. Minus RT is this integral here. So then you look at it and see that F naught is the price of the call price at time 0. And Ft basically is the call price or the call value or the payoff at the maturity T, which is given by this max function here. So you can actually see that the risk neutral valuation approach that we have talked about earlier in this lecture basically is consistent with this equivalent martingale measure approach. Now I'm going to ask you a question that under the Black-Scholes Merton framework, interest rate is constant, but in general, you can have interest rate, the risk-free rate be stochastic. And so if that's the case, you can't bring it out. You have to keep it there within the integral there. But then the question is that if R, the instantaneous risk-free rate, is stochastic, why do we say the money market account G has no risk? Right? There's something about risk-free and there's something about stochastic. Like stochastic doesn't sound like risk-free. Stochastic has something uncertainty there, right? Has some uncertainty. So how do we put together the uncertainty with risk-free? So how do we reconcile those two, right? So what is the reason? Well, if you look at it, the reason is that if you look at a stochastic process and a process has risk is because it has a volatility there, right? So which means you know the value at xt, but then you have some uncertainty about what the future value of x at t plus delta t because of this random innovation there. Now for money market account, although R is stochastic, but R at RT is known. And because RT is the rate of return, then we know G T plus delta T. If delta T gets released, at the limit delta T approaching 0. So because you know RT, the instantaneous rate there, and is the instantaneous value of any G a little bit after GT, as the GT plus delta T of that limit as delta T goes to 0 is actually known because you know this RT there. What you don't know is obviously then the next period, what is the realized RT? But then once you know that, you will then know the continuous one, the one right after that, what is the G plus delta T1, right? So the two concepts are not contradicting to one another because we're looking at, we're saying G is risk-free. We're not saying R does not have volatility, right? G instantaneously doesn't have a volatility.